Everyone, today I'm going to be providing the topological proof of the fundamental theorem of algebra based on the paper Proofs of the Fundamental Theorem of Algebra by Matthew Steed. I read this paper and thought it had a very nice argument, and I wanted to provide a visual intuition so that it's easier to understand the ideas of the proof. So first, just to restate the fundamental theorem of algebra, it says that every non-constant single variable polynomial with complex coefficients has at least one complex root. If we consider a polynomial p from the complex plane to the complex plane, there exists at least one number z for which p of z is equal to 0. We can rephrase this through an inductive argument to say that for any polynomial, it can fully factor into this form where we're just writing it in the sense z minus z to the I, where z to the I is a root. This follows just from the fact that first we can factor one root from our polynomial with the fundamental theorem of algebra, and then we'll have a new polynomial which has another root we can factor. And we can do this up to n times to get n roots. I want to point out a few things before we get too deep into the proof. The first is that this statement is not true for other fields, such as the rational field or the real field. Indeed, you can see just by the simple example z squared plus 1 that polynomials defined over these fields don't necessarily factor. And so any proof we come up with must use properties of the complex field fundamentally. For this reason, most proofs of the fundamental theorem of algebra are not purely algebraic. They usually involve some complex analysis or some topology. The naming comes from when solving algebra referred more to solutions of polynomials, and therefore guaranteeing the existence of solutions was quite important. Now it's less aligned with the more group theoretic view of what algebra means. We're also going to assume that every polynomial is monic. We can assume this because given an arbitrary polynomial, we can factor out the leading term and obtain a monic polynomial. And it's straightforward to show that the roots of our original polynomial are exactly those of our corresponding monic polynomial, and therefore if we prove the monic has roots, we prove that the original polynomial has roots as well. Lastly, we're going to assume that the constant term a0 is not equal to 0. In the case that it is equal to 0, we're able to factor out a z from every term, and we have that z equals 0 is a root. And so this case is immediate, so we can focus on the more complicated task. Lastly, I'm going to provide a definition. Throughout this proof, I'll refer to circles in the complex plane and the image of circles. Whenever I refer to a circle here, I mean a curve of the form gamma of r, which maps from the unit interval to the complex plane, and is given by this closed form re to the 2 pi it. You can see visually two circles here with radius 1 and radius 3, which just wrap around the origin one time in the complex plane. So at a high level, what we're going to do is assume for contradiction that there's some polynomial p which does not factor. P is a map from the complex plane to the complex plane, but if it had a root, p of z would be equal to 0. Since there's no roots, there's no z for which p of z is equal to 0, and therefore p is really a continuous map from the complex plane to the complex plane without the origin. So this will be the crux of our contradiction, because what we'll show is that there's a very small circle around the origin for which the image of that circle under p is homotopic to a constant. Then we'll show that there's a very large circle for which the image under p of that circle is homotopic to a curve which wraps around the origin n times. And both of these homotopies will be in the punctured plane without the origin. Finally, I'll argue that since p is continuous, these two curves themselves should be homotopic in the punctured plane. This will be a contradiction because we'll have shown that we can make a homotopy between a point and a curve wrapping around the origin n times in the punctured plane, but we know that these are different elements of the fundamental group, which I'll show at the end. This will be our contradiction, and it'll imply that p must map to the origin for at least one point z. Here's a diagram of what this looks like. Again, we'll just start with two circles in the complex plane and consider their images. We'll show that the image of one is homotopic to a point, and the image of the other is homotopic to a curve wrapped around the origin. Through transitivity, we'll have the point homotopic to the curve, and this will be our contradiction, implying that this homotopy does not exist in the punctured plane. The first homotopy we'll define is a homotopy between any two circles. So hopefully it's relatively immediate that for any two concentric circles, gamma of big R and gamma of little r, we can define a smooth homotopy just by linearly interpolating between the two radiuses, as you can see here. On the right-hand side of each slide, I'll try and include a visual diagram of what the homotopies look like. You can see here we're just shrinking and expanding a concentric circle from the large radius to the smaller one. The more significant step is to say that the image of these two circles is homotopic to each other under P. The reason for this is also fairly immediate. We can take our original homotopy H1 and compose it with P. It's not hard to show that if we consider the endpoints t equals 0 and t equals 1, it evaluates to P of gamma of little r and P of gamma of big R. But more significant is the fact that the composition of these two continuous functions is continuous, and that this homotopy lives entirely in the image of P. Since we've assumed for contradiction P never goes through the origin, this means that this is a nowhere zero homotopy, and therefore these two curves are homotopic without going through the origin. Hopefully on this diagram on the right, you can see why immediately this is not true. What I've done is I've taken our two circles of radius 1 and radius 3, and I've mapped them under an example polynomial, p of z is equal to z squared minus 4z plus 5. And the claim is that there's a homotopy between the image of these two circles without passing through the origin, which is simply not possible. We'll formalize this with a third homotopy, but before we get to that, just to recap, what we've done is taken two circles and considered their mapping under P, and claim that we can still preserve the homotopy just without going through the origin. And that is what this diagram shows. So now what we're going to do is show that we can take the image of our small circle and map it to a point. We'll do this by picking a very small radius r, such that the image of gamma of r does not contain the origin. We can do this because, recall, we assumed that a naught is not equal to 0 and p is continuous. This means that we can find a very small delta for which if the absolute value of z is less than delta, then we must have that the image of z is sufficiently close to a naught. And specifically, we can ensure it's within half the distance of a naught, such that p of z is never equal to 0, and it never gets close to 0. This allows us to define a smooth linear interpolation between the two curves, which never passes through the origin, as you can see here. So now we've got that this small circle can be made small enough to actually shrink it down to a point. And this gives us homotopy number 3, which is this correspondence. Now for our fourth homotopy, what I'll do is argue that as z goes to infinity, the polynomial's behavior is dominated and determined by its largest degree term, z to the n. In particular, there's some large radius r for which if the absolute value of z is greater than r, it implies that the image of z is sufficiently large as well. Then we can define a homotopy between the image of this large radius circle under P and a loop of radius r to the n, which wraps around the origin n times. So something that's important here is the fact that this curve is wrapped around the origin greater than 0 times, which is to say that because the leading degree of because we've assumed our polynomial is non-constant, n is greater than or equal to 1, and so this curve must wrap around the origin at least once. And formally, this is what our homotopy looks like. The argument for why it never passes through 0 is just through a simple triangle inequality, but at a high level, we've just chosen such a large radius that we never get sufficiently close to the origin, and therefore never have to pass through it in order to define our homotopy. Lastly, what we're going to do, just for nicety, is we're going to take the last curve, which had radius r to the n, and shrink it down to go through the point a0 and have radius a0. This homotopy is fairly simple. We just need to linearly interpolate between the two radiuses, but we'll pay a little bit of attention to what our starting angles are, just because there's no guarantee that under P, the image of these two circles need be aligned at the same starting angle. And so we'll just extract the real component and the angle of R, and then we will linearly interpolate between the real valued radiuses and the angles to get a smooth homotopy as follows. Again, pay attention to the fact that this homotopy is between two curves which wrap around the origin n times. So that completes this stage of our diagram, and now we're ready to derive our contradiction formally. Namely, the final conclusion is that through transitivity, we must have that the point a0 is homotopic to the curve a0 e to the 2ni pi t, where n is greater than 0. To prove this isn't the case, we're going to define a covering map. A covering map is a projection from the complex plane to the punctured plane in this case, given by f of z equals e to the iz. Essentially, what we do is we view the complex plane as a series of sheets which are all disjoint and project down to the punctured plane via this mapping. This is a continuous and surjective mapping with the property that every open neighborhood U in the punctured plane has an inverse, which is written as the disjoint union of open sets which are all homeomorphic to U. Essentially, if you've taken complex analysis, what we're doing is taking a branch of the logarithm function. You can see, since what we're about to do is essentially define a inverse function so that when we compose it with e to the ix, we recover our original functions. We're essentially going to define a continuous branch of log and pick the starting point x such that a0 is equal to e to the pi x. Then we'll argue that these two curves, when starting at the same point, if they were truly homotopic, should end at the same point in the complex plane. This is a proof you can show for generalized covering maps, but what we find is that when we define the logarithm of our two curves a0 and e to the 2 pi in x, or a0 e to the 2 pi in t, we get the curves x and x plus 2 pi nt, and we can see that while they start at the same point, they end at two different points, and therefore are not homotopic to each other. This means that our original curves were not homotopic, and so we conclude that a0 is not homotopic to a0 e to the 2 pi int in the punctured plane. This can only mean that since we showed our original two homotopies on the left-hand side and right-hand side were valid in the punctured plane, that the middle homotopy does not hold. And really what this means is that this homotopy must live in the full complex plane. This means that the image of P must contain the origin, and therefore P has a root. This concludes the proof of the fundamental theorem of algebra using a topological argument. Thank you.